Today, we're going to talk about geometric probability, section 9.6. So, geometric probability today, section 9.6. Two big important things that come up on a lot, especially on standardized tests. Geometry comes up a lot, probability comes up a lot. So, when you put the two of them together, you're going to get a lot of questions that are very similar to both. Okay, so geometric probability today, section 9.6. Well, that's out of order. All right, so geometric probability. The theoretical probability of an event occurring is the number of outcomes in the event over the number of outcomes in the sample space. So we all know, like, probability of rolling a dice. Like, what's the probability of rolling a 1 on a dice? 1/6, right? Those are like your basic probability. Okay, we can all do the basic probabilities. A lot of times they use, like, quarters. You know, flip a quarter, what's the probability of getting a heads? 1/2. Those type of probabilities, right? Well, today we're going to talk about geometric probability. So we're talking about geometric shapes and geometric reasonings with respect to probability. So the geometric probability of an event occurring is found by determining a ratio of geometric measures such as length or area. And then geometric probability is used when an experiment has an infinite number of outcomes. For instance, we can use geometric probability to represent length. A point is chosen randomly on AD. Find the probability that the point is on BD. Well, first off, you want to find the total length. What's the total length of this segment? 12. Notice they give you 12 right here. And then it wants me to find the length of BD. So what's the length of BD here? 10. So the probability of it falling on BD is 10 out of 12, or 5/6. That's geometric probability. Same thing is used to represent angle measures. Use the spinner to find the probability of the pointer landing on the 160-degree space. Well, when you think about it here, a full circle is how many degrees? 360. Nice job. So when you're talking about a circle and a spinner, a lot of times in degrees, you're going to have the 160 over 360, and then simplify that, and you get 4/9. Okay, so that's geometric probability. Let's look at the first couple problems. Number 1. A point is chosen randomly on EH. Find the probability of each event. First of all, how big is EH? EH is?
All of it.
Well, how big is all of it?
8.
8. EH is 8. Nice job. So the point is on FH. So we're talking specifically about FH here. How long is FH? 3 out of the whole segment is 8. So the probability of it falling on FH is 3/8. Okay. Number 2. The point is not on EF. So if I look at EF here, EF is 5. So if it's not on EF, it's falling on to what, Nico, you said? 3/8. Nice job, sir. What about 3? The point is on EF or GH. So how much is EF? 5. How much is GH? 2. And because it says or, I'm going to add those, and I end up getting 7/8. Nice job. And then number 4. The point is on EG. Well, how long of segment is EG, Anna? 6 out of the whole segment is what? Which simplifies to what? Nice job. And that's geometric probability. So using geometric shapes to find this sets of probability. On the same thing here now, we can use a spinner to find the probability of each event. Now, don't ask me why, but a whole circle adds up to how many degrees? 360. Don't ask me why, but this spinner adds up to 410.
Okay.
This spinner is wrong. Okay? We're gonna say it adds up to 360 though. But if you add up all those segments, it says 410. I don't know why. Because we all understand a full circle is 360, right?
Except for people who made that.
Yeah. So just bear with me here. But we're gonna say this spinner is 360. So number 5, the pointer landing on 135 degrees. Well, I would say 135 out of 360, because we're talking about a spinner. Spinner's on the circle. So 135 out of 360, nice job. And then I look to simplify that. 135 and 360 are both divisible by 5. So I think that ends up getting me 27 over 72. 27 and 72 are both divisible by 9. Nice job. Both divisible by 9, I end up getting 3/8. Good work. Number 6, the pointer landing on 75 degrees. Well, to find that as a probability, you'd write 75 over what, Nathan? 360. And then I look to simplify. Divide them both by 5. 75 divided by 5 is 15. 360 divided by 5 is 72. Can I reduce 15 and 72 further? What goes into both of them? 3. I end up with 5 over 24. Nice job. Number 7. The point landing on 90 or 75. Well, what do you do with the or a lot of times? You're going to add them. So 90 or 75, and I add them, I get 165 out of 360. Then I simplify that. Divide them both by 5. What's 165 divided by 5? I get 33 over 72. And then I can divide those both again by 3, and I end up with 11 out of 24. Nice job. And then the very last thing, number 8. The pointer landing on 30 degrees. How would you write that as probability, Schultz? 30 over what? And then you'd simplify that to what, sir? What?
5.
No. First off, they both have zeros, right?
Yeah.
So let's just cross the 0 off. I get 3 over 36. Now simplify it. What do you get?
1
Over?
12.
Good work, sir. 1/12. Okay. Using that same information, find the geometric probabilities of these 4. Take a couple seconds and try these 4 on your own. Number 9. The point is on AB. What's the probability of the point being on AB, Bailey? 5 over 12. Number 10. The point is on AD. What's the probability of it going on to AD, Reagan? What? It is 1. Yeah, because you actually end up getting 12 over 12, which simplifies to 1. Nice job. Number 11, the point is on BD. What's the probability of it falling onto BD? What do you say, Jace? 7 over 12. And number 12, the point is not on BC. What's the probability of it not falling on BC, Amy?
No.
What?
No.
What do you think it is, Allie? Huh? It's 1/3 if it does fall onto BC. So if it's not falling onto BC, I actually get Morgan 2/3. Yeah, because it does say not falling on there, so that's 8/12, which is then 2/3. Okay. Same idea. Now try these 4. These are the spinner type problems. These ones do add up to 360, so you're good. Okay. Find the probability of these spinners. So number 13 says, the pointer landing in region C. How much is in region C, Taylor? 120 out of 360. And what's that simplify as, Taylor? What? 5 over 15. And what's that simplify to further? Divide them both by 5 and you end up getting 1/3. 1/3. Number 14. The pointer landing in region A. What's the probability of that pointer landing in region A? What do you say, Samantha? Which simplifies to 1/9. What about 15? The pointer not landing in region D. Well, how much is that then, Tiana? What would you do, Allie? Yeah. You get 295 over 360. And what's that simplify as? Anybody? 59 over 72? Nice job. And the very last one. The points are landing in regions A or B. So now what do you do with A and B? You're going to add them. So what's A plus B? 175. So you get 175 over 360. And that simplifies to... What did you say? No, it's A or B. A or B. So you get 175 over 360, which simplifies to... Divide them both by 5. What'd you say? 35 over 72. Nice job. Good work. All right, next thing we're talking about is geometric probability. Take a couple seconds to look this over real fast. All right, so geometric probability here. You can also use area to find geometric probability. These are great questions that come up a lot of times on testing. Why? Because it tests your geometry and it tests your probability knowledge. It tests two things that come up a lot. To find the probability that a point chosen randomly inside the rectangle is in the triangle. Well, to do that, first thing to do is find the area of the triangle. Okay, not a problem, find the area of the triangle. Second thing you need to do is find the area of the rectangle. Great, find the area of the rectangle. After that, then write it as a probability. So do whatever you want to hit, like the triangle, over the total area. Okay, so we're looking for the triangle out of the total area. So 9 out of 50, or the probability is about 0.18. Okay, a lot of times, what popular game does this kind of involve in? We're talking about probability of shapes, hitting shapes. Darts. Darts is a popular one. What's that on darts? Circles, right? Does anybody know what famous game a lot of people play now? Typically play a lot of times in the fall. What game is made up off of geometric probability? No. Does anybody, I don't know. The true technical game is cornhole, but bags, like in the bag game, with a circle in the middle of the rectangle, right? That's based off geometric probability. Anybody ever played the game Washers? Same thing. You have a circle inside a rectangle. It's based off the game. It's based off geometric probability. All of that is. It's kind of unique, but that's how they kind of design these games. So let's look at number 17 here. It says, find the probability that a point chosen randomly inside the rectangle is in each shape. Round to the nearest 100. So I want to find the probability of hitting that square. Well, first off, I need to find what's the probability of the square. How do you find the area of the square? Ooh, area of a square is what? Length times width, or side squared, right? So what's the area of the square come out to be? 4. Yep, the area of the square there is 4. Over, now I find the area of the whole thing. What's the area of the rectangle? 28. So 4 out of 28 simplifies to 1/7. And then it says round to the nearest 100th. So what is 1/7 as probability as a decimal to the nearest 100th? That is going to be approximately 0. Anybody? 14. That's approximately 0.14. Now, number 18. Bailey, does number 18 look familiar to you?
Yeah,
I was on your test yesterday. Number 18, the triangle here. Okay, I want to find the probability of hitting that triangle. Well, the first thing I need to do is I need to find the area of the triangle.
30.
What's the area of the triangle?
30.
30, because it's half the base times the height, right? So I get 30. Over, now I find the area of the rectangle. What's the area of the rectangle, anybody? 182. And that simplifies to 15 over 91. And then I need to find that as a decimal to the nearest 100th. So what is that probability as a decimal to the nearest 100th? It's going to be approximately...
0.16.
What did you say, sir?
0.16.
0.16, thank you. 0.16. Okay, and that's how it is with geometry, or geometric probability. And again, these are great questions to kind of challenge you in respect to you have to know geometry and you have to know the probability parts of it. Great questions. All right, take a couple seconds, try numbers 19 and 20. Now 19, what do you notice you're dealing with? You're dealing with a circle. actually do use pi. Okay, I do want a decimal answer, so do use pi or 3.14 as pi. Number 20, I will help you out. Number 20, you have a what type of shape here? Pentagon. Anytime we have a polygon, that's when we have to use our formula of half the apothem times the perimeter. So I will draw this in for you. Ooh, that's bad drawing. So this segment is 2. My interior angle is 36. And I want you to find the apothem. What trig function do you have to use to find the apothem here? You're going to have to use tangent. Okay? Take a couple seconds and try these two. Find both probabilities rounded to the nearest hundredth. So let's look at number 19 here. First thing you need to do is you need to find the area of the circle. What's the area of the circle come out to be, Amy? 200.96. Nice job, because remember it's pi r squared. And then I find the area of the rectangle. Area of the rectangle is what, Ezra? 352?
Yeah.
Right? And then I divide those, and my probability comes out to be approximately what, Nathan?
I got 0.57.
0.57. Nice job. Then I have number 20. The regular pentagon. What's the apothem come out to be approximately, Schultz? What's my apothem come out to be? The apothem?
Well, is the answer 0.34?
For the apothem?
I don't know.
I thought I had you saw it there. What's the apothem come out to be, anybody? 2.75. Nice job. Yeah, the apothem comes out to be about 2.75. And then I find the area of the polygon. The area of the polygon comes out to be approximately 27.5. Over, what's the area of the rectangle, Joe? 80. So I do 27.5 over 80, and I get approximately what for my probability there, Amy?
I don't have that.
Oh. Where's it? 0.34. Nice job. Okay. Again, the key is on the polygons, you have to make sure you find that apothem to plug it into the formula. Same idea now. Try numbers 21, 22, 23, and 24. Notice, the first one says find the probability of hitting the circle. The second one, find the probability of hitting the trapezoid. The third one is now circle or trapezoid. And then the fourth one is not the circle or the trapezoid. Don't try and do them 4 different times. Use the problems from the previous ones to actually answer these. It cuts it down quite a bit. So take a couple seconds and try these. I don't know. Number 21. What's the area of the circle? Anybody? Area of the circle is? 12.56. Over the area of the rectangle is? 60. So the probability is? 0.21. Awesome. 22, the trapezoid. What's the area of the trapezoid? It is 12. Over the rectangle is 60, which is about 0.2. Now, using that information, how do you find the probability of hitting the circle or the trapezoid? You simply just add those two, and you get 0.41. I mean, I can add these too, but why not just add the probabilities? I already have the probabilities, right? Just add the probabilities. And then number 24, not the circle and the trapezoid. Well, think about it. Like I just told Bailey, if I have 2 red marbles in a bag of 5, how many marbles are not red? 3. How do we get that? We subtracted. So if the probability is 0.41, what's the probability of it not hitting that? 0.59. Why? Because you just take 1 minus 0.41 there. Okay? And that's, again, you got to find 2 areas, and then you're done with that. Nice job. Here's your assignment.